Hello everybody. This lecture is going to be about Hess's Law, which is a new topic to thermochemistry that we do not cover in honors chemistry. Here is the target to write down. I can use Hess's Law to calculate the unknown total enthalpy change during a reaction by adding together individual baby steps that I do know the enthalpy change for. Hess's Law is basically a puzzle. We're going to be trying to put together information we know to help us figure out something we do not know. Before we get started, a quick reminder that you are not a photocopier machine, you are a note taker. So if you needed every single word in your notes, I would have printed it for you, right? I would have made a photocopy, but that's not what we need. We need to focus on taking our notes. You can always go back and add to your notes when you do your annotations. Remember, there's probably a lot more words on the slides than needed. That way you can go back to the slides and use them for studying purposes. So please make sure that you're focusing on taking good notes, not trying to copy every single thing down. So Hess's Law says in going from a particular set of reactants to a particular set of products, the change in enthalpy is the same whether the reaction takes place in one step or a series of steps. So because it doesn't matter what pathway, what set of steps you use, if I do not know what the values for some of these arrows are, what some of these enthalpy values are, but I do know the others, I can use simple algebra and add them together and subtract and things like that to figure out the unknown part. And so that's what we're going to be focusing on. Real quick, you may have noticed I started using a word enthalpy instead of energy, and sometimes that makes people feel a little confused. So let's talk a little bit about what enthalpy is. Enthalpy is related to energy, but it's a little bit more complicated than what we typically think of. So enthalpy takes into account any change in pressure and volume. So if E equals the energy we're used to talking about, enthalpy would be that energy plus a pressure volume component as well. Now, the nice thing about this class and most scenarios is that we are not performing our reactions at really high pressures. We are not performing them at crazy changes in volume. So that PV component ends up being negligible. I don't have to worry about it. So just from a practical standpoint, we can assume that the enthalpy and the energy are the same thing. It's important for you to understand that they're not technically the same, that we are simplifying things a little bit, but we won't have to take into account any correction values to, make all of our work a little more complicated. We don't have to worry about that. So as long as our pressure and volume aren't undergoing crazy changes, we can be a little bit more simple in what we do. So if you look at this diagram, we have a couple pathways here. We have our reactants, we have our products. You can either get to the products on this green line, or you can get to the products using this crazy blue zigzag line. The analogy I like is path A is me, Mrs. Farmer, trying to clean the house. I try to take as few steps as possible. I try to be systematic about it. Compare that to path B, which is Mr. Farmer trying to clean the house. He takes 500 steps and, instead of taking one trip, he takes 50 trips and, back and forth and all over the place. Regardless of the path taken, you end up at the same place, right? Path A may be a much better choice than path B, right? But you're going to end up with the same result in the end. And that's an incredibly important concept for Hess's Law. When we are calculating the enthalpy change, the energy change, we are literally only caring about products and reactant levels being subtracted here. All of this pathway stuff does not matter. So if I don't know how long path A is, but I can figure out path B, I can use that information to help me. So, one of the things that we do sometimes is we manipulate our enthalpy values because we're manipulating our equations. Because the steps to get from reactants to products don't matter, what we're going to do is we're going to combine steps we know. Maybe we multiply things or divide things to try to get calculations that add up to give us the starting and ending places that we want. So if I multiply a reaction in order to change the coefficients, what I have to do is I have to multiply that enthalpy by the same factor. Enthalpy depends on the quantity of material. So if instead of 1 mole of something, I have 2 moles, my enthalpy is going to change. So you can see here, if I have 1 mole of carbon, 1 mole of oxygen gas to make 1 mole of carbon dioxide, this is the amount of energy that's involved. But instead, if I had 2 moles of carbon, 2 moles of oxygen, 2 moles of carbon dioxide being made, I'm going to get twice that amount of energy being released, which makes sense. I have twice the material. That enthalpy is extensive, right? It's an extensive property. The quantity of material matters. We have more bonds being made and broken. We're going to have more energy being transferred. So I can use that multiplying trick to adjust my coefficients when I'm trying to piece my puzzle together in a little bit. Another thing you can do is you can reverse a reaction. So let's say I look in my data chart, in my appendix, and I have this reaction here. But the reaction I'm actually interested in is the reverse. I don't want carbon dioxide being made. What if I wanted carbon dioxide being broken apart? So what I can do is I can flip this reaction, and then instead of the energy being released, the energy would be absorbed. So when you reverse a reaction, you flip the sign. If it was negative, now it's positive. If it's positive, then it would be negative because you're going in the opposite direction. So these are 2 tricks that will allow us to manipulate our baby steps with known enthalpies to combine them into the reaction we actually care about with an unknown enthalpy. One thing that's important to know is that we use a term called standard state. So the standard state is the state of a material at a defined set of conditions. So the standard state for a pure gas would be 1 atmosphere of pressure. A pure solid or a liquid, it would be whichever format, whatever form is most stable at 1 atmosphere of pressure and whatever temperature we're interested in, which is typically 25 degrees. You'll see the appendices are usually made at that temperature. If it's a solution, we assume that the standard state is 1 molar concentration. Standard conditions, standard state is important because that allows us to know for sure, what temperatures and what pressures are being used. When we look in those appendices, we want to make sure we're comparing apples and apples, not apples and oranges, right? So they're just what people agreed would be the standard state of a material. So the standard enthalpy change is the change in enthalpy when all of your reactants and products are in that standard state. If you notice, there's a little degree symbol up here. That little circle is telling you that you're using standard conditions and standard values. You can have enthalpies that are not at standard conditions. You could have something that's at, 47 degrees or 1.4 atmospheres. But then things get a lot more complicated, right? Then whatever appendix you have in the back of your textbook may not work. You may need to go find different charts to use to get your numbers. So that little symbol, that standard change, those standard conditions, makes our life a lot easier. If it's not standard conditions, it's not standard changes, then leave that little degree symbol off. One of the things that's important is to understand that when we're doing these enthalpies of making a substance, this formation calculation, how much energy is involved when we make a compound, we are trying to make 1 mole of that compound. And we're trying to make it from its basic elements. So that may require us to do some weird things with our equation, because if we make 2 moles, it's no longer standard anymore. If we make half a mole, it's not standard anymore. So we're trying to make 1 mole of product. The elements have to be in their standard states to count. And our elements in the standard state have an enthalpy of 0 kilojoules per mole, including diatomic gases. Those are still considered pure elements. So in its most stable form, we say that it's a value of 0. So I'll show you now how we can put this all together, okay? We want to know how much energy is involved when we combust methane. So there's your overall equation for combusting methane, right? You need some oxygen gas, you're going to make carbon dioxide and water. It's a nice balanced equation. Because we're trying to use standard values, right? We're going to want 1 mole. This is some information that's in a chart that you're given. It's given to you, in the appendix. It's given to you on a reference sheet. It's given to you as a chart in a word problem. You will be provided this information. You're not expected to know it. So, step 1 of this process is we're going to try to build this overall equation by adding up these equations. These are baby steps that we know the answers to find the big equation we don't know the answer to. So step 1, we need the methane on the left side. It needs to be a reactant. So I look over here and I see, hey, equation number 1 has methane, but it's a product. That's not good. But I am allowed to flip my equation. If I flip this to make methane a reactant, I have to change the sign on delta H. So instead of being negative 74.8, it is now positive 74.8. It is going to be incredibly helpful if off to the side you have some way of telling people what you have done. If you look, I took the opposite of reaction 1. On the AP test, you have to justify what you're doing to these equations, and just simply writing opposite of reaction 1 is good enough, okay? Next, step 2. If I look at this, carbon dioxide needs to be a product. Well, look here. Reaction 2 has carbon dioxide as a product. I'm just going to put that equation in next. I don't have to flip it, I don't have to multiply it, I don't have to do anything because it's already set up with carbon dioxide as a product. That was just regular old reaction 2, there was no transformation. Now, step 3. We need water as a product, don't we? If I look at reaction 3, I have water as a product. But look, I need 2 waters, don't I? I only have 1 in this reaction, so I need to multiply it. If I multiply the water by 2, all the other coefficients get multiplied by 2, and the enthalpy change gets multiplied by 2. I have double the material, double the energy. So here it is, multiplied by 2. I now have 2 hydrogens, 1 oxygen, and 2 waters. And I have 2 times that enthalpy. If you noticed, I left the oxygen till the end, didn't I? I didn't do anything because that often will work itself out towards the end of a problem. So some of the things that you'll learn when you practice are that some elements tend to be easier to balance than others, right? So it just becomes a little bit of a game on how you like to approach these puzzles. What order do you like to do them? So now what we have to do is we have to cross out things that show up on both sides. And then we're going to add up all these enthalpy values because the overall reaction is a sum of all the baby steps, right? I don't know how to do this in one giant step, but I do have data that lets me break it into baby pieces. So if I look here, I have a carbon and a carbon on each side. Those go away. I have 2 hydrogens and 2 hydrogens. Those go away. And I'm not seeing anything else that cancels. Add this all up, and you should notice that the final equation matches what we were after, doesn't it? And now I know that 890.36 kilojoules of energy is released when 1 mole of that methane combusts. Something I did not know before. My chart, my appendix, did not have this reaction in it. It only had baby steps. And I puzzle pieced them together until I could figure it out. All right, practice problem for you. Why don't you give this one a try? We want to know what the enthalpy is going to be of this reaction here. We don't know the answer, but we have some data for baby steps that we might be able to manipulate to get our final answer. Why don't you pause it and see what you can do to transform these reactions? Remember, you can add them together, you can multiply them, you can reverse them. See if you can figure out how to put them together into what we're after. Pause so you have time to do that. All right, let's see how it went. I'll show you what the answer is and how I got it. You should see that negative 103.4 kilojoules, right, is your answer. That means 103.4 kilojoules are being released. Remember, you either need to use the word released or you have to have a negative sign there. You have to be very careful about that. We care not just about the size, but also the direction, right? We need the magnitude and the direction this energy is going. So the way I did it is I looked and said, okay, I'm trying to get this as a reactant. If I flip reaction 2, it will be on the correct side. But I need 2 moles, and this only shows me 1 mole, so I'm going to have to multiply it by 2. Then I'm trying to get nitrogen and oxygen to be products. So if I take reaction 1 and I flip it, they'll be on the correct side. So that means I need a negative sign, right? But then, since these were those standard conditions trying to make 1 mole, and that leaves us with these fraction coefficients, that's not going to work because I don't want 1/2 of nitrogen, I want 1 mole of nitrogen. So I'm going to have to multiply that by 2 as well. So I do -2 times this value, -2 times this value, add those together, cancel out anything that shows up on both sides, and I get my overall finished answer. I did not know the enthalpy change for this reaction. It was not in my appendix. I didn't know what it was, but my appendix had some baby steps that I could combine, and that's what I did. Okay. Let's try another one. This has 3 reactions this time. A little bit trickier. Give this one a try. Pause the video if you need some more time to figure this out. All right, I'm going to show you what I did. One thing I want you to remember is that if you combine things in a different order or in a different way compared to me, that's fine. Remember, 1 plus 2 and 2 plus 1 are the same answer. And so please do not get stressed out if you did things in a slightly different order than me. It's just going to depend on what your brain notices and the route that you take. So pause the video if you need another minute or two to solve this. All right, I'll show you how my brain did this problem, how I figured out the puzzle. So I get negative 11 kilojoules. I start with reaction 3 because I want to get my iron oxide on the left. Reaction 3 has this iron 2 oxide, but it needs to be flipped. It's on the wrong side. The other thing I notice is that I'm only wanting 1 mole. My chart told me about 3 moles, so I'm going to need to multiply by 1/3. I multiply all my coefficients by 1/3, and then I also multiply my enthalpy. Negative because they flipped it. Next, I want to try to get iron on the right. So if I look, reaction number 2 has iron on the right-hand side, but there's 2 moles. I only want 1 mole. I'm going to multiply by 1/2. If you notice, I do not have a negative sign in front because I'm not flipping it. I'm just multiplying it by a value. Lastly, I have a big giant mess to clean up, don't I? Lots of things need to be, crossed out, combined, things like that. And if I look, I have Fe3O4 over here, which needs to go away. It's not in my overall equation. So I need Fe3O4 on the left to be able to cancel those out. I have 1/3 here, so I'm going to need 1/3 here. But what's tricky about reaction 1 is that there's 2 moles. How do I go from 2 moles of something to 1/3 of a mole? I have to multiply by 1/6. This is where being comfortable with fractions comes into play, right? I'm hoping you practice those in your math class a bunch. So remember, you can do things with the denominators and change them around and all of that, but you need to be manipulating those fractions. So in order to go from 2 moles to 1/3, I got to multiply this by 1/6. So if I do that, these are the coefficients I end up with. Now if you look, now lots of things cancel, don't they? This Fe3O4 will cancel, this Fe2O3 will cancel. Now I'm left with carbon monoxides and carbon dioxides. If you look, you got to kind of start combining them around. But when you're done, they all cancel out. You used a lot of horrible little baby steps. You manipulated them in crazy ways, and that allowed you to figure out how much energy would be released through the equation that we were interested in. Okay? Now, typically at this point, everybody's head is on the desk, or they're groaning, or their eyes are bugging out, all stressed out. Yeah, it is a mess, isn't it? It's a giant puzzle. Some people love puzzles. Some people hate puzzles. Some people see patterns. Some people don't. Some people love fractions. Some people hate them. If you love it, awesome. You got an easy topic. If you hate it, I'm sorry. Do a little extra practice, but you'll get there, right? Not everybody has the same strengths and weaknesses. Do however much practice you need to get good at it. One thing I highly suggest is that you do not crowd and squish your work. This is a game of record keeping. You're going to need to be very careful that you don't lose track of any little coefficients here, any little fractions. So you want to make sure that you're using enough binder paper that your brain can stay organized and calm, okay? And then keep in mind it's a puzzle. Sometimes the puzzles are easy, sometimes it's simple, and sometimes they're horrible puzzles, right? But that's all it is. I wish I had more tricks for you. I wish I had more suggestions. I really don't, right? There really isn't a lot to it other than adding, right? It's kind of all we're doing is trying to add things up in complicated ways, okay? So use lots of binder paper, stay calm, do lots of practice, and ask for help if you need it, okay? All right, everybody, that is it. I hope that was helpful. Bye.